All right, let's take a look at what some of the bases that we have at our disposal and when we would want to use them. So in general, right, our alpha hydrogens generally have pKa's of 16 to about 20, which is acidic, more acidic than most carbon hydrogen bonds, but it's still not very acidic. Right? It's not a carboxylic acid or anything like that. For example, water's pKa is 15.7, so you can see it's slightly more basic than water. And so whenever we use weaker bases, not necessarily weak bases, but weaker bases, like something like a sodium hydroxide or an ethoxide, we will generate some enolate, but in our equilibrium, it's still going to favor the ketone form, the still protonated form. Now, remember, this is equilibrium, so this is still going to exist. So it's still there and it can still do reactions. But for some reactions, that's not enough. We really want our enolate form to predominate. And so we just need to use a stronger base. With a stronger base, we can have complete deprotonation and basically a one-way arrow to form our enolate, right? So we really have our enolate in stronger concentration. So it depends on what kind of reaction you want to do, whether you want to have an equilibrium of your ketone and enolate, or if you just want to have just straight enolate. The most commonly used strong base is this LDA, which looks like this. Nitrogen with 2 isopropyls, a negative charge, and then a lithium just as a counter charge, right? So LDA, lithium, diisopropyl, amide, right? In this case, referring to that negatively charged nitrogen. And again, just like other times, right, that's going to be that nucleophilic carbon right there. So if we want a one-way arrow, we just have to use a stronger base. Another one that's often used is sodium hydride. The reason that it has complete conversion is because when this hydride picks up an H+, it turns into hydrogen gas and then leaves the reaction. So it can no longer go the other way. You don't always need a super strong base to completely deprotonate. It just depends on the acidity of the proton. So for example, right here, this proton is quite more acidic than a regular alpha hydrogen. And so even here, if you use just sodium ethoxide, you'll get complete deprotonation. And if you think about why you would get complete deprotonation, it should be pretty logical, right? This one can resonate with both carbonyls, and it's so it's much more acidic.